Hello, welcome to this second part of the fifth video, which in effect is the sixth video of this series on setting up for safety analysis an airfoil for integration to the front wing of a STEM racing competition car. The last video ended up with us actually down here at the cell zone conditions, where we ensured that the working fluid of the domain, external flow domain around this NACA 0009 airfoil was indeed air. We're going to move on now is into the boundary conditions, setting these up, and hopefully through this video we'll be able to run our force calculation, which again for a quick step back is set up as a steady state model, which is something there that we can refine as our safety analysis moves on to become more real world. But certainly for this this workflow that'll take us up to mesh independent study, it's adequate. So I'm going to double click here on into the boundary conditions, and my task page brings me up specifics on them. The most important ones really to check on these will always be our inlet, our outlets of course, and check to make sure that our walls are to specification. This interior system flow field and system flow field are more or less the same. These are going to describe the flow field around the airfoil. If I come on into inlet, I can see that the type, this boundary type, and again, this inlet, outlet, wall, so on, these are the name selections that I made in, could have been video 2 or 3 when we were way back in the setting up the flow domain there, but prior to the meshing. However, inlet is a velocity inlet. I'm going to click on to edit here. And it gives me a couple of options with respect to the editing. If I take myself out of this, what we can see here, for instance, inlets, you can see arrows that are normal to my flow domain. In all cases, they're normal there. And that's the way it's defaulted to be, that you're going to specify a magnitude, and of course velocity is a vector, so the direction that is default specified is going to be normal to the flow domain. We don't want that because we're not sending air into the airfoil from all sides. This is going to be a 2D flow, and we're going to assume that the airfoil is moving along the x-axis here from the right hand side moving left, or the air is from the left moving right, as it does be in CFD. And so what we're going to do is we're going to specify that all the air is just moving in the single 1D direction. So the velocity specification on that, we can put it here into components or magnitude and direction. I'll stick it here until my components, and I'll stick an x velocity and a y velocity. So there is going to be no y velocity on this, but I want to put in an x velocity. Now you can also put it in here as your magnitude and direction here as well, where I can just specify the velocity magnitude separate, and then I could say what percentage of it is going in the x and y. It's whichever you prefer. I'll just keep it at this one here, and just for the variation. What is our velocity magnitude? Well, we want our velocity magnitude to be such that it'll work out to generate a Reynolds number equivalent to that which has been used in experiments to check the likes of lift forces or lift coefficients and drag coefficients, or indeed L over D values. So the papers there that I had looked at that I would propose that we compare our values again was using a Reynolds number of 50,000. So what we want to do is we want to find an equivalent velocity for 50,000. So what we'll do is we'll just run that calculation backwards on this one here, and what we'll look at there is we'll take our 50,000 result off a Reynolds number, we'll multiply that up by our dynamic viscosity, which is roughly 1.8 e to the power minus 5. Then we'll divide that up there, of course, by the density, which is 1.225, and we'll also divide that up by the characteristic length, of the length of our airfoil, or our boundary layer on the airfoil, which is our chord length, which will be 0.025. That's 25.25 and run that, and we can see there that we're running with a velocity of roughly 29.38. Now I'm going to make that 29 meters per second because I know that dynamic viscosity is slightly high. It's 1.78 or that. So if this value is going anywhere, it's certainly going down the ways. Now I don't know if it's density that, if density is a wee bit overestimated there, I might just pop that back up again. But I never will run with 29 meters per second onto this here. So my velocity magnitude in here, I'm going to put it in this 29, and the x component is going to be the full of that, and there's nothing in the y direction here. All right, this is handy because what I can do if I wanted to run an angle of attack, instead of changing the axis or the angle of inclination of the axis of the airfoil in geometry, what I can do if I wanted an airfoil, I suppose if you're looking at it on the screen running this road, or maybe instead of the air coming straight on into it like that, what I can do is just rotate everything in, keep the airfoil parallel to the track surface or horizontal, and just specify the air coming in this road here, which will have an x and a y component with the same magnitude. The overall magnitude, the resolved magnitude of that vector would be 29, but that would be split between an x and a y component. So that's a handy way of doing it. Right, so we'll apply that, close it. The interior system flow field, when we click into that, there's going to be nothing as such of interest looking in that. Outlet, certainly we can look at if we can just, oh sorry, I should go on in this road here, no, just a zone name, close outlet, yeah, edit that. And there should be nothing to change in this. So what we want is a 0 gauge pressure there on our outlet, so there's no resistance to the air coming out of the flow domain, right? So it's 0 gauge pressure, which is 1 atmosphere on the absolute, and we're going to keep everything here the same. Normal boundary total pressure. Prevent reverse flow, no. You see that 20 chord length out the back, we shouldn't really have any reverse flow at that stage, especially with such low Reynolds numbers, so there's nothing really ever to do on them ones there, on them options. And then finally, again, we can look at sys flow field just for thoroughness, nothing to do on this one here again, it's the very same as interior sys flow field. But wall, yeah, let's just validate that our condition on the wall is as we want. So it is a wall, it's a stationary wall of course, and we're imposing a no slip condition, shear condition for that. Standard roughness height, all that there's all right. Okay. High roughness icing, no. These will be sanded down and painted airfoils. But that said, if you do know what it is and you have maybe sanded it down to a specific grade, you might know what that is there, and yeah, absolutely tune these best you can. But what we're going to be doing for the most part is an idealized smooth airfoil at the minute. Okay, so everything's okay. I just hit apply just in case and close. And that's it. So that's the boundary conditions done for the inlet. Now the internals, the outlet, and the wall conditions. Nothing on the mesh interfaces as such to do in them. Auxiliary geometry definitions, dynamic meshing, no, nothing really much to do in a lot of them. I do tend to use myself the likes of the named expressions on these, especially where I don't write an external UDF or user-defined function, which I will be doing. I'll either be doing a UDF for the velocity profile, which would be obviously the integral of the acceleration of this airfoil as I accelerate from, or the airfoil accelerates from 0 meters per second up to a top speed before drag decelerates down to a final speed. I try to plot that profile, and instead of putting in a single magnitude into the boundary condition for the inlet condition, when I run the transient condition on it, I'll write an expression, again, which will either be user-defined file, which a user-defined function, which will be a separate C code written, and I'll bring that in and I'll parse it in this software, or else you could write it in as a named expression potentially. and you can see a lot of them up here in the top things: user-defined functions, custom field functions, and so on, named expressions. But really, these functions, you can write them in nicely there. But yeah, if time lends itself to it, and if anyone is interested in it, let me know. And as I said, I love doing this stuff, so just let me know, and I'll certainly do it. But for now, nothing on the named expressions. The solutions now within the methods here. This is something to be looked at. Coupled is what's defaulted on this one here, pressure velocity coupling. So as we'd said before, what's solved at the center of these cells is pressures and velocities. And in a lot of cases, we use pressure to help us with velocity and velocity to help us with pressure. So that's kind of what the coupled scheme does. You have the simple C in the piezo scheme. Some of these schemes are maybe more stable for different types of flow. If you wanted to know which scheme to run with, the first port of call again is going to be the Fluent Users Guide. But what we can also do, of course, is we can look back at what others have done, and what we were looking at was this paper, which laid out what the let me just come back on into this one here again, how the computational setup, the computational procedure. C-shaped domain, structured grid. So he used 10 chords, or they used 10 chords ahead and 20 behind, where we have 15 chords ahead. Boundary condition was no slip to the airfoil, 3 increasing fine grid resolutions. They had only about a third of the cells that we have. Nope, but they didn't say what method they used, or what discretization method they used. But we'll stay with the coupled method for this one here as well. Spatial discretization on this, second order is fine for pressure, second order up one for momentum. Okay, so the higher the orders on these here, the it is a Taylor series expansion as far as orders of accuracy that this keeps. So the second order is always a good one. It's a more accurate one. And what that's really doing is calculating values in a cell, which is taking the values on the cells around it to converge in it, as opposed to looking at a linear solution. We're looking at more of a quadratic solution for that one. So yeah, everything looks okay in that. But when we run the calculation, we'll be able to follow the convergence of the criteria that we set for convergence, and if we see any sort of instabilities, we could look at different sorts of schemes here as well and see which one would work best. But again, the ANSYS Fluid Guide will, our users guide will give good guidance for the likes of an external flow application for airfoils at these lower Reynolds numbers, or where you're at transitional flow and using a specific model, turbulence model, which ones lend itself to it. I tend to always start with the coupled one anyway, and yeah, we'll see how we go with that one. So that's the method. Now the controls have relaxations in them as well. If this really comes down onto the convergence, if things are getting very tight to converge, what you can do is you can adjust the relaxation factors here as well to help it a little bit. But at the minute, and where should you adjust them to? Well, again, go back into the ANSYS users guide, and that will generally tell you if you should increase or you should reduce the relaxation factors and which ones you should do. But generally, I wouldn't touch anything to do with our densities or body forces, usually the pressure and the momentum, which will lend itself to the velocity that you can move. But again, for this sort of application where we have a very well resolved mesh and all, there shouldn't be any call to have to do much with them. Report definitions here are important. What we want to do is we want to add in more report definitions here, specifically for lift and for drag. So what we can do is we can add in a new force report, and here's one here for drag. So when we open up this force definition, and this is going to output us a variable on drag, and we can do drag coefficient or drag force. I'm going to stay with the drag coefficient itself, and so what we'll call this one here is going to be drag underscore coef. Per zones, no. The the force factor, the drag is all going to be acting in the same direction as the flow coming on to the airfoil, and the airfoil is parallel with the flow, so everything's going to be in the x direction, so all components are going to be in the x, which is that's 1. Report file, report plot. I want to create an output parameter in this one as well, because I haven't created any parameters just yet for my meshes or say dimensions in my geometry setup, but it is something that I will do. It just takes more time, because what we do is we take in a parameter study as well, so we do multiple design points and compare our values. It's important there for the mesh independent study in that. But again, if it's something there that's of interest to others, let me know, and we'll certainly make videos on that as well. The frequency here, so whenever this is when this is moving towards a convergence, how often do I want to know what the drag coefficient is? Now this frequency says here for every single iteration, it's going to give me a report out. I don't need it for every iteration. Every 5, 6, I'm going to put it down to every 12. Okay, just again in a multiple of 6. I'm going to go every 12 and just output me what your value's at. And of course, I want to do it here on the wall, which is my airfoil. That's where the drag coefficient's acting. Okay, so there's one definition in drag coefficient. I'm going to put another one for obviously lift. Force report, there's lift. So same thing, it's going to be a coefficient. Let's call this lift coef. And of course, we can make a named expression for one of these here as well. We can create our own variable, our L over D factor, just by dividing obviously the drag into the lift. So yeah, so here you can see the x is 0, and because it knows it's a lift, it's defaulted here to put all the force or the direction of lift normal or perpendicular to the direction of flow, which is right. The lift, is at 90 degrees to the flow, hopefully. Where drag there is, along the axis of flow. So that stays there at 1. That's fine. That's what the report file will be called, brilliant. That's what the plot will be called, brilliant. And again, I'm going to create an output parameter. I'll print this on the console as well, just so that we can see what's going on. And again, frequency 12 is fine. And this is acting on the wall. Okay, done. Right, so there's 2. Now I can add in more. I might want to look at, I could set up a point on the airfoil, some X over C ratio point, and look at pressures at that area specifically. That's absolutely brilliant. You can do that because you'll see that in a lot of experimental data as well. But for the minute, drag and lift is really all I'm going to look at now. And then when I run the solution, I will come back, and I'll also want to look at my y plus values as well. Don't forget that the y plus, or the first cell height that we calculated there was based on a target y plus value. I believe I had it in at 0.6. Might actually still have it here. Yeah, y plus target was 0.6, but our velocity was 30. We're running with velocity, I think we said was 29. Actually won't have much of a difference. We'll have a bit of a buffer there, but we can see how our y plus has resolved over the length of the airfoil. Okay, so that was the report definitions. I dropped them down. I can see the 2 I added in. The monitors, let's get a wee look at the monitors here. I have residual and report files. So in my residuals here, my RMS values, I'm going to look at continuity, x velocity, y velocity, my turbulence, energy, omega, intermittent. So these are the 4 equations in my turbulence model here, and we want them 4 equations to converge to a certain R. All right. So for definitely, I'm going to bring these down to 1e to the power of minus 6. 6 again. Okay, the likes of these turbulence ones, maybe not so much. I don't need to bring them down as much. Right. I might not get these ones. I'll bring these down slightly less. And things you might see these again, depending on the pressure velocity coupling with the pressure velocity relationship in the solver. You might see these oscillating, but we'll see how we go on. So that's it. Now I can add in, these are convergence conditions here for me to stop iterating, but I can add in more convergence conditions here. And what I will do here, just for thoroughness, is I'll try to get my lift and my drag coefficients also to converge. I'm going to add in, so report convergence 1. I'm going to say converge lift. Port definition, there's my lift coefficient, stop criterion, and again I'll try to get that 1e to the power minus 6 on that one. Ignore iterations before 0, so we could say there, let's just in case for some reason I get 2 successive iterations that happen one after the other. At the start, for whatever reason, I'll just ignore them. So that's probably going up a wee bit high. I'll just go for 6 on that. Use iterations, so just 1. I'm just going to keep the 1 on that one there. I want all conditions to be met, and every iteration there is fine. All right. And I'll add in another one, and I'll go for converged drag. Converge drag, and same thing, except that's the convergence there. I'll go for 1e power minus 6. Let's run for 6 there. That's fine. Residuals, you can click on that, but that's just going to bring you back into the into this page here, the residual monitors. Okay, and okay. So that's now everything that I need to converge on in my monitors. Report outputs, I selected them to report files out, and then they will save into my into a folder, a subfolder in the folder that contains this workbench file. So again, it's very important there again that if you are saving this on OneDrive, I said this a few videos earlier, that you make sure that them files are available all the time. So you need to select that on locally in your local directory in your C. So nothing else really to do onto this one here. What I do want to do as well is my reference values. I just skip over that one, especially because we're dealing with lifts and drag coefficients. This is like an initialization, but it's asking me where do you want me to take data from. So there's a couple of things there we can change and tie up on this. My reference values is 1. That's what it's defaulted to. It's not really that. But what I can do is I can drop this down and look at my inlet conditions. And when I do that, I can see my velocities popped up 29. Now the area here, the reference value of the area over that, that's given in as 1. This is a 2D analysis on this one here. It's a thin Airfoil. So normally what I'm going to do is I'm going to put that in as my chord length. The density of the air looks good. The depth is just 1 into the screen there. Alright, enthalpy, length 1 meter. I think all that there is okay. I don't think the length has much to do. It is really the area one, I think, that has the that has to do with the lift and the drag. But anyway, we're going to try that one there. So that's them all done. And the reference frames, that's all done. Automatic cell registers, all that there's done. Now, and coming on into initialization. I used to like standard initialization, and I would have computed there from the inlet and initialized that using 29, but I've kind of gone over into the hybrid. But what I always do on that is I go into more settings and I put the number of iterations up till a 20. It's just what I do. I hit play on that, hit cancel and close it. Now when I initialize it, we'll see it coming up on the console here, what our values are coming down to. So hopefully these come down into the -8s and -9s. It's taking a wee bit of time, longer than I would have thought that it would have. But there it goes. We're just about to, yep, now we're going into the -8s when we hit 10. So we'll even make -9. Somehow I just don't think we will. That's alright, that's still fairly good. Hybrid initialization is done. That could be some sort of an indication there how our calculation is going to perform. But however, we'll see what it's done. So what it's actually done when it's initialized is took the values at my boundary, and what it's done, it's given a value into each cell. Each one of all these cells here, the 500,000 odd cells. So the very fact that there is 500,000 odd cells is enough to think that maybe that's a reason why it took so long to initialize. Calculation activities, nothing really much to worry about in there. Autosave, execute commands, these are just preferences, I think, for the most part. Now I'm going to come on into run calculation. So the setup for this one here, when we're doing a steady flow, steady state flow, isn't just as detailed as what you do for transients, because we're not setting time steps in this one. But the time step method is going to do an automatic time step method, let the solver decide itself. Length scale method, conservative time scale factors 1, that's fine. Now, the number of iterations on this one here, we're just going to be doing this for one big long section of time, as opposed to a number of iterations per time step. So what I'm doing this here is set this relatively high, set this up to 1,000 initially. Profile update, so how often, how many iterations, or how frequent during my iterations do I want to see an update on the graph. 1 is fine on that one. All right, so I should just see this, my graphs changing as they go. So I'm going to run on into calculate here. Hopefully it doesn't take too long, but if this is starting to run a wee bit slow, going through the iterations, and it doesn't seem to be converging so quickly, I might just put you onto pause and then come back whenever it's completed. The speed at which this is now resolving. Okay, let's get a wee look at the task manager here, where we're at. All right, I'm using half my memory at the minute, 31.3, and CPU 7%. Oh, it's just doing so bad. Now we're running the calculation now. Okay, so I should hear the fan on my computer starting to ramp up. Okay, let's get a wee look now at what's happening. So my CPU percentage is way up to 50% now, and my memory is still holding steady at 50%. So it's a nice even balance there, what I'm using in virtual memory against CPU power. Okay, what do we have in here now? With coefficients, just not seeing. Let me see what's happening. Scaled residuals, what's happening with them? Velocity is starting to converge there very quick in the X. The Y velocity is coming down, so those are the ones I knew would come down fairly low. Turbulent energy is coming down. They're all coming down to fairly low ones. Continuity never seems to come down at the same rate or to the same levels. Now, I set an awful lot of convergence conditions on this here, so it's not only the continuity X and Y components of velocity, turbulent energy, omega, the intermittent transitions, and the RE theta, the Reynolds thetas there. I've also set in there that the drag has to also come down, has to be iterated to a certain level, so I can see where my drag is running to there at the minute, and my lift is coming up here. So we're at a 0 angle of attack. I would expect on the lift to have 0 lift thereabouts, albeit it's remarkable that, just as a pure aside, that the NACA 0012 or 0012 aerofoil shows a negative lift characteristic at specifically a Reynolds number of 50,000 at a 0 degree angle of attack, and it has stall characteristics as well. It's an odd airfoil for that matter. There's an awful lot of papers done out on the NACA 0012 for that reason. So if you are using an NACA 0012 airfoil as part of your stem racing solution, whether it be on a front wing or a rear wing or winglets or anything like that, just be careful of Reynolds numbers of 50,000 and its behavior. That 12% chord thickness, or 12% of chord for a thickness, is something that you're looking at. Yeah, NACA 0012 will do it, but you might have another option there as well to look at, which will not be as sensitive to developing laminar separation bubbles, especially ones that might not necessarily reattach. Okay, so this is taking a wee bit of time. I'm only up to iteration number 60, so what I'll do, as promised, is I'll pause this. I'll see is then when this is finally converged. Just checking in again, and as I thought, it is continuity that's the culprit. It's the only one I'm waiting for here, but it's coming down fairly quickly. I'm down to 4.85 by 10 to the minus 6. So when it hits down below 1 by 10 to the minus 6, I'm there. But everything else has come down phenomenally low. It's converged exceptionally well, especially the drag coefficient. Now I'm approaching 10 to the minus 12 on that. So yeah, a couple more seconds, hopefully continuity will catch up with the rest of his comrades. Okay, I'm going to come back, and what I'm going to do is I'm going to stop this here, because I'm not going to let it run out to 1,000 iterations. I'm satisfied that it's converged adequately enough. I was maybe over ambitious with my targets, especially for the continuity. As you see, it did come down fairly low, and now it's just starting to go up a wee bit. So it did come down there as low as 1.4. 1.4 odd there before it starts coming back up into the 1.5, 1.6s, but it is very well converged. Everything else there looks good as well. Scaled residuals, there everything's looking phenomenal. Very good there now. Drag coefficient plot, that looks to be fairly well resolved there as well, converged, as does my lift coefficient. So what I'm going to do, instead of running this out to 1,000, I don't think it's going to get much better. I'm just going to hit stop down here. And that has run 192 iterations, and I'm just going to let this collect the data and do a level of publishing for me when it catches up on it, and then when I've confirmed that that's happened and everything is looking okay, I'll stop this video, because we're coming up now over the half-hour mark, and the next video what we'll do is we'll look at the results of this and compare that to the published data. This is still trying to stop. Maybe I missed that. Sometimes with this video recording software, it just seems to skip over. There, stop. That's it there. I just wasn't clicking it when it goes into the corner. It just doesn't. This doesn't seem to register the click. So yeah, a minimization and moving the window into the middle seems to fix that. So now it's collecting the data. We'll see how we go with this one. So what we will do when we get this is we'll look at the contours, and what we'll do is we'll look at the lift and the drag coefficients, compare that to the experimental data for this Reynolds number and for this angle of attack, and see how it compares. Now we would expect that our lift coefficient, this should be 0 at a 0 angle of attack. Selig in the University of Illinois does publish only the lift coefficients. It doesn't publish the drag on that, so we can't really look at that paper, but there is another couple of papers there as well that I have found. There's that complete that I have found, which do give indications of drag, whether it be by drag explicitly or by the L/D metric. So it'll actually be a nice one to do there as well. We might write ourselves up here and name the expression, or even a function there, and we'll create a new variable in L/D and see how that compares itself. L/D is a nice metric to measure an airfoil's performance for a given Reynolds number and an angle of attack. And what we'll also do is we'll check our Y plus values here along the airfoil as well, along the length of the airfoil, when we get back into the next video. So again, thanks very much. I hope the second part here, in conjunction with the first part of setting up the solver, was useful, and you picked up a good couple of pointers, things that you might choose to adopt yourself, and maybe other things that you might choose to avoid, whether something I do or something you were going to do. But at any rate, yeah, let me know how you get on. I am interested in it, and if there's any problems, of course, just drop anything into the comment. I will deal with it. So yeah, thanks again, and see you in the next video.